There it is. All right, so we did the equation. Now we're looking at a graph. We're still doing particle motion. So the number one thing that you should do before you start a problem like this is make sure that you really know what the graph exactly is. Is it f? Is it f prime? Same thing with an equation. Is the equation f for f prime, and is the table of values f for f prime? Because depending on what it is, you're going to use it differently to answer questions, as you'll see. So here it says the graph shows the position y of t of a particle in inches. So we have units moving along a vertical line from 0 to 7. Okay, so now we have, instead of moving on the x-axis, you can imagine something is going up and down on the y-axis. And this is the graph of its positions in inches at any given time second. So this is the position. So what would the slopes of this graph represent? You might want to orient yourself before you even start. This would be maybe something you do in your head. Y values are the positions, the vertical positions, and the slopes are the what? What's the derivative? Slopes are derivatives, right? What's the derivative of position? Velocities, right? Yeah. So that's how you orient yourself. That's how you're going to use it. So the y values are the position, and the slopes, which are the derivatives, are the velocities. Now, normally we can't compute, slopes of a curve without the equation, but this is a pretty common thing to give you something that is a piecewise linear, because the slopes, being straight lines, you can calculate it by just counting rise over run. Okay, so we will be able to find the slopes, which are the velocities. Okay, so let's take a look at question A. On what open intervals from 0 to 7 is the particle moving down? Justify. So you can either answer the question and then justify, or you can justify ahead of answering the question. Let me show you what that looks like. And this helps yourself answer the question, by the way. So a particle is moving down when its position is decreasing. Would you agree?
Yes, sir.
Okay, and that's going to be when the velocity is what? Negative. So particle moves down when y prime of t. You can't just throw v of t out there, because v of t is not given to you. It's not defined anywhere. So someone might mistake v of t, which is velocity for us, as like vagabond of t. I don't know. So if you define it though, when y prime of t, which equals v of t, is less than 0. So now you've just defined what v of t is. But you don't need to do that. You can just say when y prime of t is less than 0. Okay. This occurs, right? This occurs on. And now we can answer the question. So we've given ourselves something to look at. If we know the slopes of the y values and we want to know where the derivative is negative, we want to know where the slopes are negative here, right? Where this function is decreasing. And it should be on those intervals, right? On the open interval from 2 to 4 and the interval from 6 to 7. This one is actually kind of nice if it's moving vertically, because you can almost imagine as the graph goes down, it's crawling down, whatever. So 2 to 4 and then 6 to 7. 2 to 4, 6 to 7. On 2 to 4 and then union 6 to 7. And are there any units on that? Seconds, right? So that's how you can answer it. Instead of using inequalities, you use interval notation. If you want, you can even spice it up by adding, like a t epsilon in front, but it's not required. And did we justify? Yeah, we did it in front of answering it. So the justification is going to be this part right here. That's the justification. Justifying usually means using some type of math terminology or math notation to support your answer. Okay. Whereas explain, if it ever says to explain, that means use your words. Find your words and use your words. Okay. You could change the world. On what open intervals is the particle at rest? Justify. Okay. So let's try to answer it and then justify it. But you can tell yourself what you're looking for. A particle's at rest when what is what? When the velocity is 0, and if the velocity is 0 slopes, it's when the slope is 0. Do we ever have 0 slopes? Yeah, from 0 to 2, right? Now notice this particle is changing at crazy rates. There is a sharp turn at 2, there's a sharp turn at 4, there's a sharp turn at 6. So that's where the derivative doesn't exist. That's where the velocity doesn't exist. This is very improbable in real life for something to change directions instantaneously like that, but we can make it happen in a graph quite easily. So 0 to 2, so the particle is at rest, particle is at rest on the interval 0, 2 seconds, units on that. And then because, now you can justify it on the back end, because can we use V of t now if we wanted? Yes. Now you can use V of t because you defined it, because V of t is less than 0, or I'm sorry, equal to 0. Equal to 0 on this interval. And again, that's a judicious use of the pronoun, right? The antecedent is clearly defined up above. So however you prefer. The justification is the V of t equals 0. And that's mathy. It has a little math in it. At what times does the particle change directions? Justify. Particle changes directions when, yeah, essentially when there's a sharp turn, but it has to be, the slopes have to change signs, right? Yeah, from negative to positive or positive to negative. So does it really change directions at 2? It goes from not moving to moving downward. That's not a change in direction. That's just an initiation of motion. So we wouldn't say that. But notice at 4, their slopes go from negative to positive, and at 6, they go from positive to negative. Now, again, before I became an AP reader, I would have clumped those together and just say, since V of t changes signs at both of these. But no. College Board wants to know how the sign changes. And unfortunately, they both change in a different manner, don't they? So we have to justify each of them independently. Kind of a bummer, but we'll do it, okay? So let's start at 4, right? I got to start farther to the left over here. Particle, complete sentences, right? Particle, or the particle, you can do particle, it's fine. Particle changes directions. We're answering like engineers now. Particle changes directions at t equals 4 seconds. You can group them both together if you want to do it like this instead of one at a time. At t equals 4 seconds and t equals, I'll try to pull this off, and at t equals 6 seconds. Okay, so there's the answer, and now the justification, because v of t, which I can use now again, changes from, I got to come up here and look, negative to positive. You don't say decreasing to increasing here, right? You never really justify anything by saying the words increasing or decreasing. That's not justification in their eyes. It's always about a sign or a sign change. So because v of t changes from negative to positive at t equals 4 seconds, and from positive to negative at t equals 6 seconds. Right. And notice we don't have to say anything about the particle, the velocity equaling 0 there, because it doesn't exist. It literally changes directions instantaneously. So that's how you can kind of group them together. You justify them separately, but you can answer them together. It saves a little bit of writing rather than doing 2 separate arguments. Okay, but you got to say what the sign change is. Good to know. During the first 6 seconds, what's the particle's displacement? Explain what this means in terms of the particle's change in position. Okay, so displacement, I'm going to call it DISP. It's final minus initial position, right? Final position minus initial position. So no, displacement is a vector. So the sign does matter. You leave the sign. And that's why you always have to do final minus initial. So I'm going to go ahead and write it out like this. Y of 6 minus y of 0. So that would earn you points right there for the setup, right? Using the notation that they gave us. They said the position is y of t. And now I'm going to grab those values off the graph. Y of 6 is 0. Here's 6. Y of 6 is 0. And y of 0 is 6. Oh, that's funny. Aha. So this is 0, and that's 6. So when I get my answer, I get -6, and then there's units on that, right? We're talking about inches. Inches. So there's the numeric answer, and now we answer the question, and you always start with the moment in time or the interval of time. So you could say during the first 6 seconds, that's their word, so that'll work. But let's try this. From t equals 0 seconds to t equals 6 seconds, comma. I don't know if that's less writing. Either one would work. The particle is displaced. That's a good word to use, is displaced. And now we answer it like a vector. So magnitude first and then direction is displaced 6 inches down. Yes. Downwards. Yeah. That would work. I like downwards. Kind of implies movement. Or you could say 6 inches below where it started. You know, there's a lot of different ways to say that, where it started. Downwards would be kind of the easiest way to do it. Yeah. Okay. So it's a vector. We have the magnitude and we have the direction. Okay. All right. During the first 6 seconds, through how many inches does the particle travel? Is that the same as displacement? No, it's not, right? So this is the one where we have to calculate the absolute values of the displacement between turning points, okay? Now, you don't have to show the setup for that. You could actually go up to the graph and look at it. So the distance, I'm just going to label it as distance, is equal to, so it's during the first 6 seconds. So we're still looking on this interval. So pretty easy to figure this out again, because it's moving vertically. From 2 to 4, it goes down how far? From 6 to -6 that's 12. And then from 4 to 6, it goes up from -6 to 0, which is 6 units, right? So here's what's kind of cool. If you write those on your graph, those numbers, if they appear in your calculation, that's enough to indicate your method. Okay, so if I just write 12 plus 6, I can actually stop there if I put units. But those numbers, when they're seen above, it's like, oh, okay, I know what you did. So sometimes they don't require the justification. Like in here, it doesn't say to justify, which means if you could do it in your head, you could answer the question directly. So you could have just said 18 inches. But remember, it's always good to try to indicate your method, because they up their standards every year. And, you know, it's all about communicating your results. Remember that. It's not just getting the right answer. You want to convey to someone looking at your paper exactly how you arrived at that decision. Okay? So when in doubt, do not leave it out. So it traveled 18 inches to net 6 inches below where it started, right? That's what we just decided. Okay, what's the particle's velocity at t equals 5? Is that average velocity or instantaneous? Of course it's instantaneous. It's at a moment in time. Explain what this means in terms of the particle's movement. Okay, so this is the one that we can interpret 2 different ways. Now, it probably wouldn't say movement. It's going to either say in terms of the particle's position or in terms of the particle's velocity. Okay, so we'll answer it both ways. So I can actually write v of 5 now, or y prime of 5, either one. But because I've named v, I can use it. I can use it forevermore. So v of 5. I'll come up here and I'm like, okay, it's the what of the graph at 5. The slope, right? So we could calculate the slope of that line pretty easily just by counting. Let's count rise over run. So the line segment anywhere. So I'll go to this point here, which I know is at -6,4, and I'll use that point. Those are the 2 points I would recommend using, because the others are just kind of vague. So from there, I go up 6, right? Up 6 and right 2, right? Up 6, right 2. So just writing a little +6 + 2, that's enough to indicate the method. So rise over run, and that equals 3. So that's the slope of the line segment. Now, normally we want to show a difference quotient. Like if it's an equation that they give you or a table of values, you're going to be expected to show the change in y over the change in x. But in this case, you didn't have to necessarily write the ordered pairs and then show the difference quotient. You certainly could have. Okay, but if it's a graph, you can count it out. And what are the units there? Inches per second. Good. Inches per second. You can abbreviate inches, right? IN and seconds typically. I know sometimes we just use S, but SEC is okay too. You just want to be careful not to over abbreviate units, right? Like put I divided by S. It's kind of like, well, that's how we do it in my house, right? Go a little more, right? Now in the sentence, we don't do that. So let's go ahead and say it in terms of position. We'll do in terms of position first, okay? At t equals 5 seconds, at t equals 5 seconds, comma, the particle's position is whatting. It's increasing because that's the rate. Good. Position is increasing by 3 inches, right? And we don't use the slash there because we have to answer in units of what we're describing. So you could say per or every. I'm going to go with every second. You could say per there. That's fine. At t equals 5 seconds, the particle's position is increasing by 3 inches each and every second. It's good. All right, in terms of the velocity, which they also could ask, same thing. At t equals 5 seconds, get that out of the way with units. The particle is moving, right? There's motion. And is it up or down? Up. At, and then we can go ahead high, at 3 inches per second. Halloween costumes for the yearbook. The Scooby-Doo, we need the whole Scooby-Doo bunch. And anyone who else has a costume on. Bilky, you've got horns on. You don't want to come, you don't want to be a devil out there? Trap you? Oh, yeah. They're going to meddle in your affairs, right? Yeah, meddling. Yeah. All right, go ahead and try to answer the rest of them so we can move a little quickly when we get back. I think you got the idea, right? No, it just means it both.
No, I just don't understand. Oh, yeah, like that's the one. Yeah, well, I think that.
Yes, I don't see that. Look, literally on the ground. Look. Up 6. That's 6. Oh, government.
Rocky, you better come back here. Why?
Come back.
Oh.
riser 1 equal to 672. Like the same as the
You
last.
still roll. You're wrong. That's what I'm saying.
No, you did it on that line. It's gonna be the same slope in the whole line.
So all the ways to remote people are just like one
Hi,
Gavin.
Velocity is like, I think of velocity as time,
Hey, Gavin,
distance divided by time.
turn on your mic.
Oh.
Oh, hurts.
Oh, isn't it velocity distance divided by time?
Which one? I did the wrong words. What? Speed or velocity?
Speed of that.
I did.
Is that what you
Yeah.
Right?
I'm so smart.
Oh, no. What's it called? Velocity.
Don't worry, sir.
I did.
G-Rich.
Yeah,
Okay, any questions on the second sentence? We can use the diagonal there because we're talking about moving, right? Whereas up above, we're talking about its position. They mean the exact same thing. So you just have to read carefully which one it's going to say. It won't just be vague and say movement. Okay, what's the particle's velocity at 5.9999? Yeah, that's right. That's still on the same line segment, isn't it? So it should be the same as 5. So all we have to do is say V of 5.9999 equals 3 inches per second. Okay, so notation is everything. You don't want to just write down 3 inches per second. Okay, you don't want to do that. So either Y prime of 5.9999 or V of that. And then at 6, V of 6 is what? Is it 0? There's a sharp turn there. The slope from the left does not equal the slope from the right. So it's actually DNE, yeah. It's not differentiable there. It's a sharp turn. So again, this is a change in direction that is impossible for us to achieve as mortals, okay? All right, we lost a Zoom member. Kaya had to drop out. Okay, all right, bye Kaya. She'll watch the video. Hi Kaya, if you're watching. During what open intervals is the particle's speed the greatest?
When the slope is the greatest magnitude, this occurs in 2 seconds. 2, 3, 4.
Oh, yeah, okay. Very good. Speed is the magnitude of velocity, and if velocity are the slopes, then we just want to know over what interval is the graph the steepest, right? In any direction? Not necessarily the most positive, but the steepest. So did we calculate the slope from 2 to 4? No, so it would be down 12 and right 2. Okay, so that's the slope of -6. And then the slope from 4 to 6 was up 6 over 2. So let's go ahead and write that. We could do the work right here. That's fine. -12 over 2 is -6. It's our work. And then here 6 over 2 is 3. And on this last segment, we go down 1 and right 1. So that's going to be -1 over 1, which is -1. Oh, it's 3. Yeah, 3. Sorry, my bad. Ay, caramba. That was bad. That was bad of me. Good catch there. Good catch there. So it's -3. All right. So now we look at those numbers, -6, 3, and -3, and we look to see which one has the greatest magnitude, right? Which is, of course, 6. And that occurs from 2 to 4. We don't have to step over 3 because it goes straight through it. So that's fine. So we can just say from 2 to 4. So you could say the speed or just speed is greatest. Talk like a caveman. That's fine. Speed is greatest on the interval from 2 to 4 seconds. Now, did it ask for us to justify here? No. So you could volunteer it if you want. It would be because on this interval, the graph is the steepest or the slope has the greatest magnitude. I think that's what you said, right, Jacob? Something like that. Yeah. Now, here's the deal. If you justify and it doesn't ask and you say something incorrectly, then you will get docked. So you always have to speak the truth, okay? Now, on what interval is the velocity the greatest? Is that the same question? No. So now we want to know, and I'll just write that out here. Let me just write the speed is the greatest is going to be the steepest, okay? Velocity being the greatest is when the slopes are the most positive, or if there are no positive slopes, or the least negative. Sometimes there are graphs where all the slopes are negative, and then you pick the one that is closest to 0. Okay, or if you have a positive slope, you pick the largest one. Okay, but it's kind of crazy because you could have a slope like this that's super steep, like from A to B. Let's call that A to B. And then you can have just a real gentle rising slope like that from B to C. Okay, and of course the speed is the greatest from A to B, but the velocity is greatest from B to C, because no negative number is going to be bigger than a positive number. Okay, so now we don't want to look at just the magnitudes. We look at the actual signs, and which one's the biggest? +3. Okay, so that's going to occur from 4 to 6. Okay, speed is the greatest on that seconds, and we can just tag it on here. Velocity is greatest on the interval from, and I forgot already, 4 to 6. Yeah, 4 to 6. That sounds right. 4 to 6, what? Seconds. Yeah, you got to be careful with the units. For a question like this, they might make the units just worth 1 point on a free response. And if you miss it anywhere or put the wrong units, like you put, moles per liter or something instead of seconds, you'll lose 1 point total. But sometimes the units are connected to the correct answer. And so if you don't have the units each time, it's like a whammy, whammy, whammy. All right, and then finally, what's the particle's acceleration at t equals 3? Particle's acceleration at t equals 3. This is kind of a good head scratcher. 0?
Yes, because there's no change in velocity. It's constant velocity on the interval.
That's beautiful. That's it, right? Yeah, yeah. You were working while we were out there having fun taking pictures, I could tell. Yeah, no, that's exactly right. Acceleration is the rate of change of velocity. So if the velocity are the slopes, then the acceleration would be the change in the slopes. And as Jacob said, there is no change in the slope at 3 because it's on a line segment. And we learned all the way back in Algebra 1 that a line has a constant slope. It does not change, okay? So I would just say V prime of 3. If you want to go ahead and define that as A for this last problem, you could do that, okay? It's 0. And it doesn't ask you to justify, but it's always good to be prepared to justify, whether it's in math or in life, right? Say what you mean and mean what you say, and be able at any time to justify or defend, whatever the case may be, your opinion or your actions. Yeah, if you can't do that, maybe you shouldn't be doing it. Yeah. Okay, so pretty nice little question. Again, that whole thing would not be a free response. It's a little long, but any component of that could be put together into a free response. And of course, any singular one of those could be a multiple choice question. So any comments or questions on that? Like zoinks or Ruby, roll. I can't do the zoinks very well. my voice is cut. Can you do the zoinks, Colin? That's Shaggy's trademark, right? Like, let's get out of here, school. Okay, Raggy. I don't know. There you go. There. You know I like Scooby because he's my alert on my phone. Yeah, I like Maxwell too. Yeah, yeah. You're doing a good job portraying him. I might say. Okay. Moving on to the next one. I'm yelling again. I could tell my voice starts getting a little scratchy. Ah, there we go. There we go. Use the technology. The graph above shows the what of a particle? The velocity of lux. I can't do that. All right. In feet per second. Okay. So now we have to use the graph a little bit differently to answer the same types of questions. It's moving on a horizontal line this time instead of a vertical line. And it's from 0 to 6. Okay. And we have seconds. So again, we're on unit alert. So if you come up here, you might want to again orient yourself. You could say it in your head, or you can write it down. The y values are the velocities, and the slopes are the what? Are the accelerations. Good. Now this is probably the most common type of question that you're going to be given, a velocity graph, because the velocity is in the middle of our derivative chain of kinematics, right? Position, velocity, acceleration. And so from the velocity, you can answer, of course, questions about velocity. The derivative gets you to answer questions about acceleration. And when we learn the second half of the house of calculus, which is integration, that's anti-differentiation. It's going backwards. And so from this graph, we will be able to actually obtain position values. It turns into, just kind of a preview of coming attractions, it turns into area problems. Y'all might know that from science or whatever. But if you notice, when you find the area, you're multiplying, right? And if you multiplied feet per second times seconds, the seconds divide out and you get feet. So it turns out that the areas under the curve are the positions, the y values are the slopes, or the y values are the velocity, sorry, and the slopes are the accelerations, okay? So pretty cool. You can reach everything from right there. Okay, so let's see. Letter A, on what open intervals or at what times, because it could be at a single moment, on the open interval from 0 to 6 is the particle at rest. Okay, so again, the particle's at rest when the velocity is 0. The velocity now are not the slopes, right? The velocities are the y values. So where are the y values 0? At 1 and at, let's see, this is 4 and 5, so that must be 4. If I make the dot big enough, I could call it 4, right? 4, right? No. So this is another common thing that College Board will do. A lot of the times they'll cross at a nice integer, right? They'll have a grid pattern, or they'll, like this, it'll cross the x-axis at 1, indubitably. But if it's not like 100%, you know, on that mark, then you can't assume. It could be 4.1, it could be 4.2, it could be something else, right? We can find it because that's a straight line. Okay, I drew it, I didn't snap it straight, but it's a straight line. So let's go ahead and write the ordered pairs here. If I can find the equation of the line, I should be able to find its x-intercept. Agreed? So a little miniature problem, like a game within a game, all right? Those are fun. So this is like 3, -6, and then this point up here, the other definitive one is 5, 4. So here we go off to the side, bench work, right? So we have the points 3, -6, and the points 5, 4. We only need a point and a slope to find the equation of a line. We have 2 points, so we can choose either one of them. And from those 2 points, we can easily get the slope, right? So let's reminisce about Algebra 1. 4 minus -6 and 5 minus 3. Or the other way around, right? -6 minus 4 over 3 minus 5. I just always like to do the bigger x value first because it reinforces final minus initial for displacement. Okay, so this ends up being 10 over 2, which is 5. Okay, so now, which point do y'all want to use? 5, 4 or 3, -6? Okay, y'all use 5, 4, and I'll use 3, -6. Okay, we should get the same answer. So now I'm going to use that point, and I'm going to drop it in Taylor form. So you don't have to do so on your bench work, right? It's your bench work. So y equals the y value of -6 plus the slope m, which we just found to be 5, times x minus the x value of 3. Now, how do we find the x-intercept of any function? We plug in a 0 for x? Good. It's the y value that's 0, so if it's equal to y, we set it equal to 0. And now we solve, right? Solve that algebra. So I'll bring the 6 to the other side while I distribute the 5. So distribute the 5, 6 comes across, 15 goes across, it becomes 21. Divide through by 5, and you get 21/5, which you're more than welcome to leave it like that. But as a decimal, that's equal to what? The easiest is probably to multiply by 2 over 2, right? Because then you get 42 over 10, which is 42 tenths, which is 4.2. Or you can go off to the side and do division, right? 5 goes into 4 one time, 1 left's over, bring down 0, 5 goes into 10 twice. However, I don't know, it depends, you know, it's a preference. Do you want to use terminating decimals or do you want to use fractions? I kind of like the fractions. But I think in this case, I'm going to call it 4.2. So there it was. So I don't know. I was thinking 4.1, but it ended up being 4.2. I was close, right? Close doesn't earn me any points here, unfortunately, right? That's statistics. Okay, so now I can answer the question. I want to know where the particle is at rest. That's when the velocity is 0, and that's now at t equals 1 and 4.2. So let's go ahead and answer the question. Particle is, can we say resting instead of at rest? That's kind of cute, isn't it? The particle is resting. Shh, answer quietly. At t equals, oh, I forgot again. 1 and 4.2, okay. At t equals 1. Is it seconds or hours? I've got seconds, okay. At t equals 1 second. And at t equals 4.2 seconds. Because it said to justify, so because v of t equals 0 at these times. Okay. And again, you can answer or justify ahead of answering it, right? Particles at rest when v of t equals 0, period. This occurs at t equals whatever, because that gives you something to look at. So it's kind of nice that way. Either way, doesn't matter. Whatever you prefer. Just make sure that you put units. Uh-oh, what did I forget? I didn't put units on my 4.2. Oh, gosh, diggity doo dog. Okay. So maybe I only lost 1 check for the whole problem. So if I know I left it off, I can either go back and add it so I get the point back, or I'm just like, oh, well, I'm past that point. No looking back. And now I can just start using whatever units I want. Crazy units, right? Like moles per liter, furlongs per fortnight. That's a great one, right? A fortnight is how many weeks? 2, yeah. Fathoms per millennium, whatever, I don't know. Adnams, do you have one in mind, like a crazy unit? No? Yeah, I would say that you can go back, right? As long as it's in the same problem, you can go back and add the units. So you might want to check before you leave. Now, there are 2 sections on the actual AP exam, and they're closed. So the first one is going to be 2 questions with the calculator. I'm sorry, the multiple choice section is closed. The first 2 questions are free response with the calculator, and you have 30 minutes. Then you put your calculator away, and then there's 4 more questions without a calculator, and you have an hour for those. But you are still allowed to go back to those first 2 questions, which you originally had the calculator for. The only catch is now you don't have the calculator. So you could still go back, though, and preview them and look at, or review them, I should say, and try to catch little notational errors like units and stuff like that. So the multiple choice sections, they're closed. So you'll take, like 30 questions without a calculator. That section's closed, can't go back. And then like 15 questions with a calculator, and then you can't go back.
On the multiple choice, do they look at your sign work at all?
None. It's graded by computers. Right answer, wrong answer. Okay. So, yeah. So what I was telling the AB class, because as they were working those questions, I was noticing that a lot of them were not, there were multiple choice questions, obviously. They were not using the proper notation, and I kind of asked them why. I'm like, oh, I know, and it's like, it's not going to be. So it's not going to be graded. But then I told them, I said, you know what, if you don't practice the proper notation, what are the odds that when it matters that you're going to be able to produce that, right? Very, very unlikely. But look at the other side of that coin. If you do practice your proper notation all the time, then on the multiple choice, when you know it doesn't matter, then you can elect to not use the notation. It doesn't take any training to not use notation, right? But it takes training to be able to use proper notation. So you should always, when you're practicing, whether it's free response, multiple choice, quizzes, whatever, you should always try to use proper notation because it's easier to jettison than to acquire, right? Miraculously. Okay. Because then when you're not doing notation, you're willfully and conscientiously and consciously and purposefully leaving something off, right? Whereas if you're just like, I think this is how you do it. Oh yeah, I didn't realize I was supposed to have that there, right? You know, okay, so I'll get off that one. But yeah, good. They don't look at it at all. It's just machine graded. But they hire people like me to sit there and look at the free response questions very carefully, you know, to score it where notation does matter. So anyway, about half the teachers that grade them are high school calculus teachers, and the other half are about they're college professors. So they like the mix. On what open intervals from 0 to 6 is the particle moving to the right? Particles moving to the right. Justify. Hey, let's justify ahead this time. Particle moves right. Moves right when, good, when v of t is greater than 0, comma. This happens or occurs, whatever you prefer. This occurs, two C's in occur. This occurs either at or on. Let's see, so velocity equals greater than 0, greater than 0. So that's where the graph is above the x-axis. Yes, yes? So in there, look at there. Yeah, yeah. Now, did it say open intervals here? On what open intervals? Okay, good. Because, oh, it did say open intervals here too. Yeah, because notice, I could actually, if it didn't say that, I could actually include t equals 0, right? Because at t equals 0, where the graph exists, it is a positive velocity, okay? So you would be able to include that, but you would not be able to include 1 if it didn't say that, because at 1, the velocity is not positive, is it? It's what? 0, okay? So again, we'll just say this occurs on the interval. We don't have to write the interval. We just say from 0 to 1. And then when we put seconds there, that's what makes that an interval, not an ordered pair. And that's what makes it an independent variable, a t value, and not a y value, right? The units, they kind of are a substitute for saying t epsilon. But you could put t epsilon if you want. You could even do this, 0 less than t less than 1 seconds, right? If you're an inequality type person, you could do that. Doesn't really matter. I like the interval. It's real easy, right? Parentheses. Okay, sweet. On what open intervals or at what time is the particle moving at its greatest speed? Greatest speed is going to be the greatest magnitude of velocity, right? Oh, crap, there was another one, right? I got so excited. Yeah. There was another one, 4.2 to 6. Thank you. Oh, my gosh, I'm so embarrassed. So you could just tie those together. Thank you. I was trying to make a point. My brain has not been getting a lot of oxygen today, to tell you the truth, inside this costume, so we'll just blame it on that. Okay. But thank you, Mia. Very diligent. Okay. And then, of course, you could do, if you did the interval notation, then you would say 0 to 1, and, or and. You could say and there because in that case, it's an English conjunction, not a math symbol. 4.2 less than t less than 6, and then you can put seconds. But interval notation is pretty sweet. So let me make sure I answered the question now. Oh, yep, those are the only two places where the graph is above, so that's good. All right, where is it moving at the greatest speed? So that's going to be where the magnitude of the y values is the greatest, yes? So that's going to be where the graph is farthest away from the x-axis or the t-axis in any direction, right? So above the t-axis, it gets as high as 4, right? So that's 4 feet per second. But on the negative side, it goes all the way down to -6. So that's a speed of 6 feet per second in the leftward direction, yeah? So the answer is at what? T equals 3, yeah. So we'll answer that. So the greatest speed is at t equals, and dang it, I forget all the time. 3, there we go. 3 seconds. Does it ask to justify? No, so you don't have to. Now greatest velocity, now the sign matters, right? Now the sign matters. So now we're looking to see where the y value is the highest on the graph, not in any direction, but literally up. And that's going to be where? It's going to be on the interval from 5 to 6. And did it say open intervals here? Yeah. So it's also going that velocity at t equals 0. Does it say what time or at what points? That's one of those things that you probably would not lose points if you added it, because it's not an untrue statement. If you, like when you list 3 decimals, that's the minimum. You can always list 4 decimals if you want, and as long as they're correct, that's good. So you can always go above and beyond. So let's just say, go ahead. Oh, yeah. See, right here. Yeah, you're right. Thank you. I knew there was something on there. Very good. Now, had that been like that with equal signs, then you could include 0, no penalty. But yes, thank you. Thank you. Man, this is a good teamwork today. The greatest velocity on the interval from 5 to 6 seconds. Let me double check. 5 to 6 seconds. So what I've seen before is multiple choice questions that look like this, V of t, and they have t over here, and they have a, let me move this up. This is up here, and they have something that goes like this, then it goes, and like this is A, this is B, this is x equals c, this is d, and then the endpoint is e. And it asks you at what x value, A, B, C, D, or E, is the speed the greatest? And of course, the answer is what? At D, right? That's where the graph is farthest away from the t-axis. Where is the velocity the greatest? At B, yeah, at B. Okay. What if it, instead of doing that, what if it did this? And now we had more values. The speed would still be the greatest at that point, right? At D, the speed would still be the greatest, but where would the velocity be the greatest? At E and at A, if it starts at 0, yeah, because 0 is bigger than any negative number. So again, if all the values are negative, in this case we have 0, if all the values are negative, then the greatest velocity would be the least negative, the one that's closest to the t-axis. Okay, excellent. I'll catch on quickly. No justification needed. On what open intervals from 0 to 6, non-inclusive, is the particle speed increasing and decreasing? Oh boy, speed increasing, decreasing. These are the fun ones. For velocity increasing, you just look at see where the slope is positive, because that's acceleration. But remember, speed is a scalar quantity, so we have to look at not just one thing, but 2 things, okay? So the speed is going to be increasing when the y values and the slopes, this is just thinking out loud, are the what? Same sign or opposite sign? Same sign. Good. And they could be both positive or both negative. So let's see if we can go catch that. All right, so I'm gonna highlight the interval. So from 0 to 1, I have positive y values, but I have negative slopes, right? That's not good. So let's go ahead, we can actually, let's just put a D for decreasing, okay? How about from 1 to 2? We have negative y values and negative slopes, yes? So that would be speed is increasing. We do have to step over 2 because there's a cusp there. It's not real pronounced, but the slopes are different on each side. So from 2 to 3, again, negative y values, negative slope, so the speed is increasing. So from 3 to 4.2, we have negative y values and positive slopes. Those are opposite signs, so the speed is decreasing. From 4.2 to 5, we have positive y values and positive slopes, which is increasing. And then from 5 to 6, we have positive y values and no slope. So that's where the velocity is a constant. So if we highlight it, it's on those intervals. So I'm going to answer it right here. Speed, and then I'll bring it down there. Speed is increasing on the intervals from 1 to 2, union 2 to 3, and then union 4.2 to 5. Now, could we just go straight from 1 to 3? No, because we're comparing the y values to the slope values, and what's the value of the slope, or what's the derivative value at 2? It does not exist. There's no acceleration there. So you can't compare velocity and acceleration if acceleration doesn't exist. So little things like that, and then we'll do seconds. Did it ask us to justify? Yeah, it did. So this is going to kind of be not fun. But remember, the real justification that I used to say is just because on these intervals, you know, the y values and the slope values are opposite sign or same sign. They don't want that anymore. They want to know what the signs are. So we have to do two arguments, right? So because on, or how about this? Because v of t is less than 0 and v prime of t, which now if you want to call that a of t, it's up to you, is also less than 0 on the intervals from 1 to 2, union 2 to 3, and then v of t is greater than 0 and v prime of t is greater than 0 on the interval from 4.2 to 5. So again, you're not going to necessarily have to find all the intervals on a free response because they realize that's a lot of writing. So they might just say this, on the interval from 1 to 2 is the speed of the particle increasing and decreasing. And so you'd say, oh, the speed is increasing because v of t is less than 0 and v prime of t is less than 0. Yes, Colin. Oh, yes, I need to put seconds down there. I did miss that. Gosh dang it. I was thinking of what I was going to say next. Did not run through the tape at the end of that race. Thank you, Colin. Colin, I'm like staggering at the finish line, and Colin picks me up. My legs are trembling underneath, and he's dragging me across the finish line on that one. Thank you, Colin. All right. You're a very unselfish runner. Yeah. Okay. And then we could do. Do you want to write it out for the decreasing, or do you got it right? Yeah. Let's just say it. Who wants to say it? Nose goes. I thought Colin raised his hand first. I didn't see it go to his nose. I just saw his hand shoot up. So Colin, no, you're off the hook. You just helped me across the finish line. Why don't you pick someone? Max, you want the microphone for that?
Oh, no, that's okay.
Okay, all right.
Um,
Can you do it in Scooby's voice?
no.
That'd be hard, yeah. I'll start you off. Speed is decreasing on.
On the intervals, speed is decreasing on the interval 0 to 1, and for the unit sign 3 to 4.2.
Good. So if you're at home, Scooby-Doo is doing this one. Max will do. From 0 to 1, union 3 to 4.2 seconds, comma, because
V of t is greater, V of t is less than 0, and V prime of t is greater
okay, on what interval?
on the interval 0 to 1.
Oh, now that was the 3 to 4.2 interval you were doing.
Oh, okay.
Yeah, because v of t is less than 0 and v prime of t is greater than 0 from 3 to 4.2, and then do the 0 to 1 justification.
V of t is greater than 0,
V of t is greater than 0
and V prime of t is less than 0.
and v prime of t is less than 0 on the interval from 0 to 1 seconds. Ruby, roll! You get a Scooby snack.
Maxwell, if you want, you can go to the freezer and get an icy pop. There's icy pop if you want.
There's icy pops in there, and the scissors are in there. So well done. Yeah. So it would be a lot of writing, but again, in reality, you would only be asked to look at one interval, like the interval from 0 to 1. Okay. But if we don't prepare answering it for everything, it's not going to be easy answering it for anything, right? Okay. So good. That was good. Okay, so we're on letter E. Letter E. How are we doing on time? Plenty of time? 350, yeah, okay, good. What is the particle's acceleration at t equals 4.8 second? That should be seconds. And then explain what this number means in terms of the velocity. Okay, so the acceleration at 4.8, 4.8. 4.8 is going to be right around here, right? And of course, the acceleration is the what at that point? It's the slope, right? Yeah. So kind of like what we did before when we were finding velocity by counting slope on the previous one. Now we're going to count the slope, but it's going to be the acceleration because we're essentially one rung higher. So we could just count it, right? We go from -6 all the way up to 5 for a raise of 11, right? So up 11. And then we run from 3 to 5, which is 2. So it would be 11 over 2. Okay, so I wrote that up there, and I put dotted lines, so I can just come down here and say V prime of 4.8, which equals A of 4.8. Now, if I had actually answered the previous question this way, you know, where I actually, right in here, remember, I defined A of t. So now you could just use A of t if you want, okay? But you can't just pull V and A out of a hat. You have to define them because it's not a universal truth that, you know, V is velocity and A is acceleration. A could be azimuth or something like that, right? So A of 4.8 is 11 over 2. And what are the units? Inches per second squared. Perfect. The units of 11 are inches per second, and the units of 2 are seconds. It's a division process. All right, so now we have to answer that in terms of the velocity. So here's the sentence, the Kolbian-Harvard sentence. At t equals 4.8 seconds, I'm going to add an S this time, comma, you don't want to, did I make some mistake? Oh, it's feet, okay. So, yeah. Good thing I already lost the unit, and that's important. I'm glad I'm making these careless mistakes because they're easy to make, right? They use inches a lot, they use feet a lot, they usually use seconds, but it could be hours. Yeah, so the good thing is on the actual AP exam, you don't have tunnel vision, right? You have, well, maybe so, if it's all online again, right? But if you have a paper right out in front of you, you can actually just easily refer back to the units without having to like scroll out and scroll up. It gets a little disorienting. That's my only objection to learning on the iPad. You get tunnel vision, and with my bad short-term memory, I get tunnel vision. And with my bad short-term memory, I get tunnel. Did I say that already? Tunnel vision. Okay. So at t equals 4 seconds, the velocity, it says to describe it, what the velocity is doing, is whatting? Increasing, right? It's a positive value. So the velocity is increasing by, and now we got to be careful here, 11/2 feet per second, right? Those are velocity units. We answer in velocity units. And then you could say per or each or every single. That would be kind of cool, right? Every, for emphasis, every single friggin' second. Oh, yeah, right? Yeah, 11/2 feet per second every single friggin' second. We look at that and we're like, that guy's confident. Right? If we saw that and we're grading it, that guy's confident. Yeah. And then he gets it wrong, right? Yeah, whatever. So that's not okay. I would save kind of let's save the showing off for the math parties, whatever. Okay. On what open intervals or at what time is the acceleration the greatest? Oh my gosh, these are long problems. Acceleration the greatest. Well, those are the slopes, right? So are we looking for the steepest, or are we looking for just the most positive or the least negative? Is it steepness? Most positive, right. There is no, I don't have a name, or there is no like speed equivalent for acceleration. Velocity is a vector. Velocity is the magnitude of that. Acceleration is a vector. What do you call the magnitude of acceleration? There's not a name for it, right? I don't know. There's not a name for it, right? So if it just says greatest acceleration, we don't even have to consider negative slopes if we have a positive slope, do we? So it looks like there's only one section where there's a positive slope, and that's from 3 to 5. Yes, yes? So it would be on 3 to 5. So acceleration Complete sentence again, caveman style. Acceleration greatest. Unga bunga. How do you spell unga bunga? At or on, yeah, unga bunga on. And dang, see, I forget again. Tunnel vision. That's a good foreigner song if you like classic rock. But it's double vision, sorry. But you can say fun, tunnel. It is tunnel vision. What am I talking about? Seconds. No disguise. No, it's double vision, not tunnel vision. Ouch. Whatever.
Kodak Black song?
Oh, is there? What are y'all singing?
Kodak Black. Free my boy Kodak.
Kodak Black.
Yes, sir.
All right, I have Brockhampton written down from yesterday, and now I got to look at Kodak Black. Okay, sweet.
Yes, sir.
All right, I'll check them out. Did it say to justify here? Do we have to justify? No, no. And then G is for genius. What's the particle's displacement during the 2 seconds? What 2 seconds? I need to fix my notes. It's on my list of things to do, but my wife keeps adding things to her list that always trump this. Right? Donald Trump. The election's next Tuesday. What's the particle's displacement during the first 2 seconds? Okay, displacement is the change in position over the change, or no, just the change in position. So how do we find the positions if all we have is velocity? Well, we kind of alluded to it already, right? What would be the units of displacement? It's a good place to start with the units feet, right? So stoichiometrically, as we already said, if you have feet per second and seconds, when you divide those, you get feet per second squared. That's acceleration. When you don't do anything with them, you get feet per second, which is velocity. But when you multiply them, you get feet, and that's the unit we want. So look at it geometrically. When you multiply an x value times a y value, right? You're multiplying feet per second, whatever that is, times seconds. What geometric shape are you actually finding? You're finding the area, right? And so there's kind of like some stoichiometric and geometric justification for what we're fixing to do. It turns out that the area, as I mentioned already, under the curve gives you the positions traveled over that interval in that direction. It gives you the displacement. So if we want to know what it is during the first 2 seconds, then all I have to do is draw a line here, and I'll find the area of that, which would be that would be a positive, right? Because it's above the x-axis, and then that's going to be a negative, because that's where the particle changes directions, right? It's going from right to left. But just looking at those two, what do you notice about the magnitude of those two triangles, areas? They're the same, okay? And they're opposite in sign, right? Because that's where we say it changes direction. So you don't really need to find the areas if you know that they're the same size, equal in magnitude, but opposite in sign. It's going to cancel out. So he's right back where he started. So his displacement is what? 0. Very good. So what is the particle displacement? Displacement is 0 what? Not inches. I got it. Feet. Yeah. And it says to justify. It wouldn't ask you to justify in this case if it's a genius question. But here's one way you could justify it. Let's actually find the area. That's a little triangular triangle, isn't it? Yeah, it's a little triangle. So the area of a triangle is 1/2 base times height. So let's try it. The base is from 0 to 1. That's 1. And the height is 4. So that's 2. So what you're going to learn when we start doing integration is if you have a graph, if you write the area inside, if it fits, I like to circle it to make it stand out. If it doesn't fit inside, you could draw it outside and draw an arrow to it. But if you write the area inside, again, you have to indicate your method. As long as those numbers show up in the calculation, you've indicated your method, you're good. And then this one would also be 2, but because he's changing direction and now he's going to the left, this would be -2, right? His velocities are negative, so he's moving to the left. So area itself can't be negative. Let's actually write that as, well, we'll do that later. I'm just going to call that +2 because I want to keep it as an area. So this is where he's moving to the right, 2 feet to the right, and then the area of that means 2 feet, but it's to the left. How about that? I like that better. You can write the areas in there, and now you can use those. So 2 feet to the right, changes directions, 2 feet to the left. Displacement is what? 0. Now, it's easy to get the distance traveled from here also as well, additionally, too. What would be the distance traveled? 4, right? Now they're all positive. 2 units this way, 2 units that way, that's 4 units, right? So now, if you had to justify, you could say displacement is 0 feet, because 2 minus 2 equals 0. And we're like, where'd you get those 2's? And we go up to the graph, we're like, aha, there they are. Awesome. Oh, this is intense stuff here. Particle motion. A lot of different things can be asked. How we doing? Comments or questions? Everyone good? I don't know if I can make it. What time? How much time we got? 13 minutes. You think we can make it? You want to shoot for it? Or you save it for later? It's a good stopping point because now we're moving from graphs to tables of values. So we'll stop right there. You have the rest of the time to, I guess, work on your worksheet, which we'll easily finish on Monday, and I will roll into the next section. We got to start moving a little more quickly. It's keeping me up at night. But your worksheet will be due on Wednesday, okay? And the notes will be due on Wednesday. So I'll go ahead and put that in Canvas right now so you get the alert, all right? All right, Nathan, thanks for being here. Gavin, you were actually in 2 places today. You were at home, and sexy Gavin was here. Is that right? Yeah, and then Devin, thank you also for being here. So y'all are free to go unless you have any questions. And of course, thanks to everybody who's here also for being here. All right.